Alright everybody, welcome to Binary Adventure, and in this video we're going to go over this really nasty x86 bug that I encountered in this program. So let me first explain this because I've gone back and forth between x86 assembly that you would see being used today, and this is not it. This is a unit test. Um, well, I don't have it up right now, but in my previous videos, you can check them out if you want. We use x64, x32 DBG, IDA Pro, and we also write some FASM code in Sublime Text, and we compile it with, or we assemble it with the FASM assembler, right? So all of those videos, we are using the 32-bit modern x86. And I also talked about this program here, which is called EMU 8086. And this uses the older original 86 instruction set, and it's 16-bit. So what we're basically doing here is we have a raw CPU being emulated, and nothing's given to us. There's no operating system. There's no anything. Like, we have to completely from scratch run programs on this thing. And you might be wondering why do I use this? Well, it's still useful because even though we don't have access to EAX, EBX, EDX, and ECX, for example, because those are all 32-bit registers, we're limited to using AX, BX, DX, and CX. And you will also see here that we're limited. There's no EBP. We have to use BP. There's no ESP. We have to use SP. But basically everything's the same. It's all in 16-bit. And one of the reasons why this is so cool is because it forces you to completely understand everything that's going on in the CPU. And also, I will use this emulator to perform tests with instructions sometimes, like I showed in a previous video. And so, for example, if you needed to write a bootloader, even if you needed to write it in x86, you could use this program for some help. You wouldn't write the 32-bit code here, but you could still use this program to for some guidance and to practice basically, because all these other fundamentals like setting up the stack, setting up the segments and everything would be required, because remember, a bootloader loads before the operating system even does, so nothing is set up for you. And that's why I like using this thing. And the other reason why I like using it, like I had shown before, is that you can step through the source code one step at a time and watch the state of the entire processor. You can even so much as view the stack by clicking stack, and you can view the flags by clicking flags. Very cool. So I'll stop that there. However, we're gonna walk through this program real quick and see what it's supposed to do, and then we're going to see a nasty bug that was happening that took me a while to figure out. And it's not very obvious if you haven't done a lot of this type of programming, and that's why it's a real pain. And it's like really, really tricky because it's one of those bugs that will actually build and run, but it doesn't perform properly. So let's first take a look at the code and see what's going on here. So I create a data segment, and I set some memory to point to this string right here. So let's go over what's going on right here, because this is a little bit different from what you might have seen in my other FASM videos, right? And the only thing really that's much different is this $sign, but let's go ahead and go over this. So we have a variable. I'm calling it oset. DB means define byte, so we're defining a byte that's pointing to the first character here, and then of course this is a string. And how does the computer know how to define a string? Well, it doesn't really. What it does is it iterates through every single byte of the string until it finds a terminating character. And in regular FASM on x86, that terminating character is 0. So in my previous videos, let's say we wanted to add the string right here, you would have seen comma 0. And just pretend like these weren't here, right? So let's just get rid of them. So in my previous videos, if we didn't want to make a new line, we just wanted to terminate the string, we'd use a null terminator by putting a 0 here. However, in 8086, which is what we're on right now, you have to use a dollar sign. So the dollar sign is basically the same as the 0 that we used to use in more modern x86. And the 13 and the 10 are the carriage return and new line characters. That's all that is. So we're just, this is basically like saying \n in C. So typically in C you do something like this. You say printf hello world \n end quote, like that. And the \n would make a new line so that if we made more text, they wouldn't just string along, you know, over here like this. So let me get rid of all that. Watch, I'm probably not even going to build now because I've been putting all these extra characters in. But, so that's what we got. So we have overflow flag set. We have another string, overflow flag not set. So as you might guess, what this program is supposed to do is it's supposed to, I was testing the JO instruction. So JO means jump if overflow flag is set. So if you don't know what the overflow flag is, basically it's a flag that gets set inside the CPU when you do some sort of math or arithmetic, like adding two numbers together, and you overflow out of the register space. So in other words, let's say a register can hold up to 256, you know, up to the number 255, let's say, and then I add 254 plus 300. Well, it's going to overflow because that's past what the register can hold. It's only supposed to be able to hold up to 255. So the overflow flag would be set. And so if the overflow flag is set, it will jump. If it's not set, in the case here, putting 99 into CL does not set the overflow flag because it doesn't overflow CL. 99 can fit into an 8-bit register just fine, right? So what the program's supposed to do is it's supposed to continue execution through here, not take this jump here, and then it will output onto the screen over the message overflow flag not set because it didn't take the jump. And this is just something I got a little bit cute here, and I define my own printf function. Now it's not really a printf function because there's no format anything. So typically a printf function is supposed to take a format specifier and do formatting and that. This doesn't really do any of that. This just prints whatever message is passed to it on the screen. So it's really just like a print function. But it's neat because this shows you the basis of how these things are actually formed from scratch. We made a from scratch print function here using the interrupt that's provided. So the way this works is there are different, in this DOS mode, which is what we're running in, the 16-bit mode, what you used to be able to do was you could place different codes in here, sort of like a syscall, and then you would call interrupt 21, and based upon whatever code you place in AH, different actions would be taken. So in this particular case, we are saying print string. That's what placing 9 into AH is, the code for print the string. And then the question is, how does the string get there? Well, we place the string, a string pointer into DX. So the pointer to the string goes inside of DX, which we get from the stack here, and then we print the string out, and then we clean up the stack, and then we return. So this call printf, after it finishes, obviously we return, so we go back down to this instruction here, and then we clean the stack up. So it's much like you've seen in the previous videos. If you don't understand that part, I suggest going and checking out the previous video where we covered how to clean the stack up in cdecal. By the way, I messed up. I was filming at like 1:30 in the morning, and I totally spaced out, and I had originally said that it was std call, but it was actually cdecal, because in cdecal you clean up the stack like this. From the caller is responsible for cleaning up the stack. So in other words, in this function, which is called start here, you know, which could also be called main, for example, we make a call to another function, and then start function is responsible for cleaning up the stack. So I'm actually following a cdecal calling convention here. Now in std call, the call e cleans up the stack. So that would be like if inside of this printf function, before we returned, we actually cleaned up this pushed data on the stack here. So we'll do another video about that, but I just wanted to correct that because somebody brought it to my attention. I'm really happy that they did, because I was tired and I wasn't paying attention. So The next thing that we do here is now we try to force an overflow. So we add 98 to CL. This will overflow out of CL, and it will set the overflow flag. And then now when we do the JO, we jump if overflow flag is set. Overflow flag is set. So we jump to OF flag set, and that takes us down here. So notice here the structure of the program here, how the conditions occur. Because we have to have jump end me down here, because if the overflow flag wasn't set here, and we didn't have jump end me like this, let's say we didn't have it, what would happen is we would just go down here and we would say the overflow flag was set, even if it wasn't actually set. But see, with the jump end me here, this would, if the overflow flag wasn't actually set here, then we would just end the program and it wouldn't display the improper text to the screen. So that's a really big thing you have to get used to when you're programming in assembly language versus when you're programming in a high level language like C or Python or something, is that you have to pay attention to where your program's execution flow is falling, and because it could fall into code that's not supposed to be getting run, and the way you stop that is by doing a jump like this, or at least that's one way to do it. So now we would call printf again. We would print out the message the overflow flag is now set, and then the program ends. So very simple program. So what we should see on the screen is overflow flag not set followed by overflow flag set, right? So another thing too is that we specify here to the CPU that this program code starts in the code segment. That's what this line does. And then we set up our own stack. We set up 256 bytes of our own stack. So if we didn't have this, check this out. If we did not have this, we would have another error because we wouldn't even have a stack. So there would be nothing to push to. And if you don't set the stack up manually, when we're in a situation like this where we have to set everything up from scratch. Like, remember, this is as if we were handed a CPU and there's no software on it at all, and we have to completely control everything. Well, we have to set up a stack in order to even push and pop and all that stuff. Now, it's a little bit different in some of the other programs we've been writing because the operating system hands us over some of that stuff by default, so we don't get to see all this. But when we're programming raw assembly like this, it's kind of neat because you get to see it. So now we're going to run this program, and one of the options we have is we can step through it line by line, or we can just run it. But I'm just going to run it, and I'm going to show you the bug here. So check this out. It says overflow flag set, overflow flag set. Well, why is that, right? Why do we have overflow flag set when the overflow flag is actually not set? In fact, you could actually see, it's kind of insanity because you can actually see if we step back through the program. I'll reload the program and we'll do it step by step. You can see that the overflow flag is not actually set. So I move 63 hex, which is the number 99, into CL. And then check this out. Look at the OF. I'll view the flags. Look at the OF. The OF is not set. And in fact, we don't even take the jump because the overflow flag is not set. And instead, we push the message, overflow flag not set. And then when we go down here and we print it to the screen, watch what happens. It says overflow flag is set. And I was like, what is going on here? Because I was looking at the CPU, I was looking at the flags and everything, and I'm like, why is it saying the overflow flag set when it's not set? So then I was like, okay, maybe there's something going on with these variables. Maybe I have them switched around somehow. And I looked at that and I was like, no, I have the proper variables in the proper spots. So then I actually went to looking at what was inside, what was being loaded down here in where we move the message pointer into DX. So let's go back a few again. Let's go back up there and check out where that happens. So let's see, step, call printf, move this out of the way. So watch closely right here, right? So now check out DX in 1 second, because DX holds the pointer to that, or it's supposed to be to the one of those messages up there, right? Well, if you look at DX, it's 14. So this is our second time around, I believe. Or no, this is our first time around. So 14 is supposed to refer to overflow flag not set. So we actually see that inside of DX. And even still, as soon as we call int21 and we print that to the screen, it prints out overflow flag set. And we can see this because if we continue to step to the program, when we go back around and we actually have to print out overflow flag set, like check this out. See, we're at push overflow flag set, push or call printf, and then when we watch DX now and we see what gets loaded into DX, it's 0, 0. So clearly, the message overflow flag set is at memory 0, 0, and the message overflow flag not set was at, I think, 13, whatever it was a few steps ago, 13 or 14 or something, right? So I was like, how is it possible that this is printing the same message twice when we've just loaded it up with two separate areas in memory? In fact, I even did an experiment, and I went back here, and I changed DX to 99. So we're actually pointing to an area of memory that's not anywhere near these messages at all. And when I single step, it still prints overflow flag set again, but it prints it over here. So I was like, what on earth is going on with this program? Well, it turns out that we had never set up our data segment. So what this means is that let's go through it one more time, and then this is all going to make a lot of sense. Okay, so we're going to step. We call printf. We go down here. We place the message, which is at 14 in memory, into DX, and we place 9 into AH, and then we're about to do the interrupt. Now, this is the thing. If you look down here at DS, we're at 700. Okay, that's because we never set data segments. So we said we're placing these variables basically inside of the data segment, but we never told the CPU where the data segment was. And the problem is that when we use these variables, what happens is these macros, basically these names, they get replaced with an offset that is calculated relative to DS. And since DS has some random number in there and not the number that we need in there, it's completely wrong, and the variables don't make any sense. It's basically garbage. Now, it just so happens that the way you actually do this is you take the data segment, a pointer basically the data segment, and you have to place it inside of the AX or some register. And then you have to move it from that register into the data segment itself. So you can directly set these. You can set the anything here. You can set the data segment. You can even set the SS, which is where the stack is, if you want. You can set the CS, the code segment, but you really need to set the data segment if you define something in the data segment. Now, if I would have defined these in the code segment, the program already knew where the code segment was, so this probably wouldn't have happened. But I had defined them specifically in the data segment, and then I never told the CPU where the data segment was. So now that we set up that properly, I want you to watch what happens. I'm surprised they even let me do that because I made a code change without stopping the emulator, but let's try it again. So let's actually emulate this now, and let's watch the difference now. So we're going to single step. We're going to go to where the print's about to happen. We move it in, and then check this out now. So you notice the data segment now has the number 710 in there. So data seg represented memory address 710. So we were basically 10 bytes behind before, and that's the reason why we were still getting overflow flag set no matter what happened, because when the program was trying to get to overflow flag not set, it was actually still up here in overflow flag set, because it just so happened to be that the data segment had pointed to 700 still. So we were in the ballpark, but we weren't actually where we needed to be. Now, when we run this, watch what happens. Overflow flag not set, overflow flag set. So the program functions properly. So it just shows you how raw this is. We actually have to set up, we're responsible for everything. We have to set up our own, we have to tell the CPU where everything is. We have to tell the CPU how much stack space, where the stack is, where the data segment is, where the code segment is, all that stuff. And if we just start defining things and we don't tell the CPU where that is, so in other words, this is a cool lesson because the way the CPU accesses things is it uses things like the instruction pointer and the stack pointer, but it's also referencing the segments in the background because those pointers are pointers that are actually pointers which are relative to the segments. So if you don't set the segments up, the CPU is just going to be completely lost. But it's scary because you can still run the program and it will just do whatever, it will just go haywire basically. But if you were paying a really close attention to the difference between the original program and the working program, there was one more instruction added here, and that is this test AX. And the only reason why I added this instruction is because the program was reliant on whether or not the overflow flag was set. But the problem is that the original assumption was that the overflow flag was not set by default. But we don't really know if the overflow flag will be set or not by default, so we can't assume that. And so what test AX does is it automatically clears the overflow flag, so that we know that from this point on the overflow flag is in fact 0, so that when we do something that doesn't modify the overflow flag, it will be default 0 and this jump will not be taken. So I just wanted to clarify that. So I just wanted to show this really cool bug. I thought it was really fascinating, and it's not something you really deal with in high-level languages. So hope you liked it. Let me know in the comments. Don't forget to subscribe and stay tuned for the next video. Thank you for watching, and have a good one.